Hi everybody, we're going to sketch a graph of the rational function by doing these steps here. The testing the function just means finding your x and y intercepts. This is a rational function, so we have to find the asymptotes. I'm going to do one right now. The vertical asymptote is where the denominator is 0. So if you set the denominator to 0, we have x equals -2. So that's going to be your vertical asymptote. And again, the reason being is 3x, and if you plug in -2, you get 0, and that's undefined. So that generates the vertical asymptote. We'll do the horizontal asymptote in a moment. Then we're going to take first and second derivatives to see what we can do with that. And then your end behavior, let's just look at what rational functions look like. So basically, they're either going to look like, especially this one, it's either going to look like this, something like that, or it goes this way. And that's what we're going to use the, oops, pretty sloppy here. That's what we're going to use the second derivative test for to see. Okay, so we get started here, and we're going to look for the x and y intercepts. So we have y equals 3x divided by x plus 2. Now, if I set my y to 0 to find the x-intercept, and you cross multiply, you're going to get 0 equals 3x, because this is going to go away. So to find your x-intercepts, you just set the numerator to 0 on rationals. So we get 0, 0. Now, since we have an x-intercept at 0, 0, that means that's also the y-intercept. So we don't have to worry about the y-intercept. All right. That would just be y equals 3 times 0 over 0 plus 2, which is 0 over 2, and 0 over 2 is 0. So anytime you have an x or y intercept at 0, 0, that also means it's an x-intercept. All right? And now we want to find we already know the vertical asymptote from the previous slide is x equals -2. And now we want to know what the horizontal asymptote is. So what we're going to do is we're going to take the limit as x goes to positive infinity and to negative infinity. Of 3x, x plus 2. 3x. And they're both going to be the same because there's... so basically, remember, we're just going to divide everything by x. Okay, so this is going to end up being 3 over 1 plus 2 over x. And remember, the limit as x approaches infinity, positive or negative, of 2 over x is 0. Because as this number gets bigger and bigger, as x gets larger and larger, this number gets smaller and smaller. It gets closer to 0. So basically, we can take this part out, and so our limit equals 3. And it's for both of these. So we have a horizontal asymptote at y equals 3. So these are our asymptotes, and that's going to frame our graph. Now we're going to take the first derivative of y equals 3x divided by x plus 2. So we do y prime equals, and you write down we're using the quotient property. Derivative of 3x is just 3. Then you do minus, then we're going to write down our numerator 3x times the derivative of the denominator, which is just 1, divided by x plus 2 squared. And simplifying that, you're going to get 6 divided by x plus 2 squared. Now we set this equal to 0. You cross multiply, you get 0 equals 6, which is not true. So that just means there's no values of x where the derivative is 0. Since the numerator is 6 and the denominator is a square, the derivative is going to be positive. That means the curve is going to also be, the curve is rising. The curve is going to be rising like that. All right. Now we have to do the second derivative. So the second derivative, we had 6 y prime was 6 divided by x plus 2 squared. And if you take the second derivative, y double prime, you're going to get negative 12. I can write this as 6 times x plus 2 to the negative 2. So when you take the derivative, you're going to get negative 12 times x plus 2 to the negative 3 times the derivative of the inner function, which is just 1. So that's going to end up being negative 12 divided by x plus 2 cubed. Now we want to set this to 0, and there's no way to do that as well, because when you do this one, you get 0 equals negative 12, which is not true. So we need to check at negative 2, because remember we have a vertical asymptote at x equals negative 2. So basically I want to see what's going on here when x is less than negative 2, and I want to see what's going on when x is positive. It's greater than negative 2. So I'm going to plug in for negative 2, I'll just plug in negative 3. So let x be negative 3. And plug it into your second derivative. So you get negative 12 and negative 3 plus 2 is negative 1 cubed. So that equals 12. So this is positive. That means the graph concaves up. All right, so for greater than negative 2, I'm going to plug in, say, negative 1. Whoops. So I'm going to have to do that here. So let x equal negative 1. So when you plug that in, you're going to get, let's do red, negative 12, and negative 1 plus 2 is 1. So that's negative. Since that's negative, a negative number, it means it concaves downward. All right. So I drew my horizontal asymptote at y equals 3. We kind of knew what the form looked like. And at x equals negative 2 is my vertical one. So basically what you know is when x is less than negative 2, it's concave upward, something like that. If you want, you could plug in some points here. We knew that negative 3 went to 12. And if what did negative 3 go to? Yeah, it went to positive 12. And we tried negative 1, and that was downward, so that means it's concave downward here. All right, so it concaves this way. And that's your graph. Thank you. Have a nice day. Bye-bye.